Right. So again, sorry. I think we are recording now. So anyway, as I was saying, so today we will cover basically the last part of for the CIFAR-10 challenge. We went over we got basically a model to run fully from beginning to end on Tuesday. But if you remember, the F1 score was pretty low, right? And so today I'm just going to give you a few additional things that you could consider playing with, right, to improve the model, okay? So basically we did, I think, an MLP. This time I'll do the architecture for a deep learning algorithm, 2-3 hidden layers. And then I will also show you how to do a CNN, convolutional neural network. And that's it, right? And then after, and also I'll show something else related to the project, the final project. And then that'll be it basically. Starting next week, we're just gonna go over more like the theory of what is this and what is that. So it'll be more, getting into the guts of the loss functions and all that. Are there any questions before we begin? All right. So one thing I wanted to show you today, I'll add a link to this, and I'm pretty sure you guys, I've shown this to you before, but I just want to show you for the term project, if you remember the final project, you need to build a model, right? So hopefully you're already thinking about this. You're going to collect some data, right? And, build a neural network and deploy it with ONNX. So really there, what I'm trying to show you is, honestly, is about deploying ONNX and everything. So the model can be pretty simple. You don't have to annotate data. You can just use a data set. Do you see that? So we've talked about this before. So what I want to show you today is that I have several examples of how to deploy models with ONNX. And I showed this to you before, but I just want to show it again. So if we go here, this is the machine learning foundations, deploy to web. All of these links are, you're familiar with these two over here, which are for the KNN averaging one. And then these four here are basically for deploying PyTorch models to GitHub with ONNX. Does that make sense? So you can reference all of these. For instance, I have this one, the wine quality, right? So basically some text boxes, okay? And then you click run, and this invokes the model, and it runs the data through the model to do a prediction. All right, so the way that these work basically is that once you finish training your model, you're just going to export that model to a file, and then that file gets uploaded to GitHub basically. And then to interact with that file, you're going to use JavaScript. So not PyScript this time, but JavaScript. So what I recommend is I'll do a demo of this probably next Thursday of how to do one very simple one. But if you want to get started, and I recommend that you take a look at these four over here. So these are really nice ones. So I think this one, although I'm using my camera right now, if you click on that, it would open the camera. And then they were doing sign language. So you would, do this and it would say the sign, for instance, or something like that. Okay, so this is an example. They're all very similar, but they're all using the ONNX module. This one, if you want to load images, right, you select on that, select an image, load it to, I don't think I have any images on here. Oh, I do have one. And it does the classification. Panda is not a panda. So if you're in, so basically these are, what you can use these as reference to develop your own application. So this is an example of loading images. There's an example here of so classify images. There's an example of just a simple adding values into text boxes and predicting. There's an example here of, as I said, loading the camera, and interacting with it. And the last one, I think it's just another wine quality one. Got it? So start looking through those, make a note of that. You can use them as reference for your final project. Any questions? Nope. All right. So that's basically the final project. And then let's now try to finish up the CIFAR-10. And really, I'm just going to point out, I'm not going to solve it, obviously, because that's what I want you guys to do. But I will show you things that you can try, okay, for the challenge. So let's kind of begin there. So I'm going to open up Scholar. Go to 365 here. Content. Here, right? And I loaded that Jupyter onto the course repo, so you can now use it. So that should be where? That should be. I loaded it. Oh yeah, they're in here. So they're under neural nets, PyTorch. And if you notice, in class CIFAR-10 challenge, this has been added now. Got it? Everyone write down where it is. All right, so this is basically the Jupyter that I'm currently working through and the one I'm going to use today. If we make any additional updates to this, I will load it also here, and I'll say like hints or something because I won't solve it. Okay. But yeah, so that's kind of what we're going to do today. All right, so not hearing any questions, let's go ahead and now open up Scholar and continue with the CIFAR-10 code. And hopefully some of you have already started to try this, right? So the first thing you should do is get that 0.0113 F1 measure, right? So you should replicate that, so that you can get going. What I like about the challenge is that it really teaches you the why. Well, I can say, oh, transfer learning is great, but you're going to be like, eh. But with a challenge, with a goal, then you start to realize, oh, this is important because of that. Okay. So one thing that we noticed on Tuesday was that it took a while to train, right? I don't remember how long it took, but it took a little bit. I had to reduce the size of the hidden layer, so you can see that that's going to take some time. All right, so we are back online. So it should be, remember the MNIST data is here, I believe. Sorry, we're using CIFAR. So CIFAR. Which one? The master? Is it this one? This is 5 years ago. Hold on. Yeah, it's whatever it says on my code, but I think it's probably this one actually from 2 days ago. Yeah, in class CIFAR-10 data. Okay, yeah. All right, let's look at the code actually. Let's look at the script. Take over here. So this one should say challenge. In class CIFAR-10 challenge 2 days ago, so it should be that. And the folder is CIFAR-10 images master, right? CIFAR-10 images master. Do you guys see that? Oh, okay. Why does it say 5 years ago?
That's probably
the creator did it. Okay, interesting. All right, thank you. All right, so let's go ahead and I guess we're gonna rerun this just to make sure everything is loaded in memory. And then I'll kind of review it, and then we can get into the final details. But if you remember, we were able to achieve 0.13, right? That's a bad F-score. I'm not going to tell you guys the highest that we have been able to get here in challenges in the course, because then I would kind of, you might reach that and not continue to make improvements, right? So the goal is to just be the winner. But hopefully by the end of today, my goal is to get this to be a little bit higher. Okay, so that's my goal. All right, so let's go ahead and run all of this just real quick. Now, I'm going to hit on the kernel here, clear output. All right, so again, just a quick recap. So load the libraries. All right, that works fine. We have a GPU, we can check that. We have this time an NVIDIA A30. Load our data. Train the data, and as you know, this is you just basically have to do this exactly as is, because you'll be using the test set basically. Print an image, so it's taking a little bit. So I will basically write down somewhere in the architecture the things that you should consider using, okay? And I'll provide a little bit of starter code to give you an idea of how they work, but it's up to you to, to try it. All right, so it's taking a while. All right, there we go. So got that. Print the image of a cat. Check the balance data set. It's good. Load it the test set. We've already done all of that. Like I said, all this code is available to you guys. Okay, the test set is also balanced. We confirmed that there's 10 classes and 1,000 each. That should be enough. So out of this is where performance and the winner will be determined. Created the data loaders. Okay, and then the architecture. Okay, so we've built a very basic neural network architecture, and we are only spaghettifying the images, right, from 32 by 32 by 3. So it gives us a vector of size 3072. Okay, unfortunately, that creates big neural networks, right, and makes it, the bigger you make it, the slower it's going to be. So we built this MLP, which basically I had to make this, remember, 20 just for it to run quickly during class time. Obviously, make that bigger, right? Today, I will do the next, another class for a deep neural network. Henry, do you have a question?
No.
Yeah, right. So today we'll pick up here basically and add a new architecture, which is going to be the DL. And then I'm going to do another thing called the CNN. And finally, another thing called transfer learning, although I'm not completing this. I'm just kind of giving you a basic idea, but they are hints of what you can try, okay, for this to succeed. All right, then we have our training loop. I think this was pretty straightforward, but I'll repeat. We have the 2 for loops. The epoch just means that we give the data set to the model, all of it, n times, right? And so that's something that needs to happen. The model sees the whole data set several times, right? And that's controlled by epochs. Then after that, because we've already created the data loader, we just load the XB and the YB, which are the batches. The B just means batch. So it's the X batch and the Y batch, right? We load that data. We needed to do, we do the actual spaghettifying here, right? At this point. And then we feed that 16 by 3072 into the model, provide some predictions. And these predictions go into this thing called a loss function, which compares the predicted and the real. And basically, once we have this value, we always invoke these 3 lines of codes, which basically do the heavy lifting. This is why PyTorch exists. So basically, this is where the derivatives are calculated and where you update the weight. So this is, I'll do some simple examples of this starting next week. And that's kind of more like the theory of how this works, okay? But for now, this is where we update the weights, basically. Does that make sense? Okay, so if I do that, so I run this, it does take a little bit, right? Then we have the core functions here where we instantiate everything. So you do 100 epochs, the learning rate is 0.01. Remember, this is a parameter that you can change, okay? And then here we instantiate the model. So if you're gonna use a deep learning algorithm, replace that with the class for deep learning. Or if you're gonna use a CNN, put in the CNN there, or transfer learning, you put it in there. Once you do that, we initialize this optimizer and we tie the weights of the model to the optimizer and provide the learning rate. We also instantiate this thing called the cross entropy, the loss FN. So this is something that I will start discussing next week. All right. And then basically we just train the model. That's it. All right. The basic architecture. And then finally at the end, we print the result. So I'll run this. And while it's running, we can start looking at the other things. Okay, so as you can see, it is training. So remember, the objective during training is for this value to go down. So it starts at 2. Ideally, you could probably get that to be 0.005. Okay? That just represents that the model weights are becoming good so that when you give it an image, the class that it predicts matches the real class. Does that make sense, guys? Any questions about that concept? Nope. All right. So it's training now. All right. So let's just leave it training there. And now let's go here to let's add a few cells. So we're just going to let it train. And now I'm going to provide basically the things that you need to do. So there are, in fact, like 2 sets of things that you can do to improve this model. Create new architectures, which basically just means create new class objects. That's one thing. The other thing is, inside the classes, you can add additional things, additional parameters that might help. And these are all theoretical things that we have to discuss. Like, for instance, something called layer normalization. So you guys understand normalization already, right? What was normalization, as you understand it? Henry, yeah, go ahead.
To my knowledge, it's a way of having each of your features having an equal stay, I guess. So like, say if like you have like 2 features, right? One is like feels very small, like actually you have to go that far. One deals with like true or false, like 1 or 0.
Yeah.
And one deals like a real number, like temperatures, and like 1 to 100.
Sure.
You don't normalize it. You're basically saying that, oh, the second component of the vector has more weight.
Sure.
Than inside, which isn't what you want.
Agreed.
AI to agree.
Agreed.
Yeah.
Very good. That's true, right? And we also want those values in general to be somewhere around between -1 and 1. That's an additional thing that just neural networks respond better to something like that. So while you guys have learned that you can do normalizations at the beginning, right, on the data set, maybe you weren't aware that actually after each layer, it may also be a good idea to normalize the data. Do you guys see what I'm saying? So how does that translate? Well, that translates. So you have to understand how the architecture works, right? So this is an MLP. So you have the input layer, the hidden layer, and the output layer, right? So where is the end of the hidden layer here? And if we look at these 4 lines of code here, Like, where would I say that's like the data just got out of the hidden layer? Out of these four. Linear 2? Well, let's look at linear 2. Linear 2 says 20 to 10. So what comes out is 10. So that's actually what? The end of the neural network. You see that? So then where would be the end of the hidden layer in this MLP?
No, what was the question?
So I'm saying, let's put normalizations at the end of each layer, right? So here we only have one layer. We have the input layer, the hidden layer, and the output layer. So you need to understand, even though you have a picture of it, of the diagram in your head, right? I have a marker here. Nope, marker. Can I see a marker here? No. All right. So you have the input, the hidden layer, and the output layer. What I'm saying is we do normalization of the original images, but at the end of each layer, you may also want to do normalization, right? So then what I'm asking is, where is the end or of the hidden layer? So,
Act one.
Act 1, after this one. Okay, very good. Exactly. So that's what that means. I wish I had a marker so I could write this down. There's not a single marker here. All right, so so you have the input layer, you have the hidden layer, the output layer. So right after that hidden layer, you want to put a normalization. You see that? What if you had an input, hidden layer 1, hidden layer 2, hidden layer 3? Maybe you would want, or you have for the board? Yeah. So this is actually important because, yeah. So what I'm saying is, we're doing an MLP, right? And you guys did normalization here of the data as it goes in. But after each layer, you may also want to do a normalization. Believe it or not, sometimes little things like that are what win or what make your model finally work. They're just little tricks that you do, okay? And so if you know you want to put a normalization there, or let's say that you have a neural network that has, yeah, better. So this works better. All right, so you have two, then you want to do a normalization here and a normalization there, but you have to know where that is in your code, right? Thank you for the markers. And so basically, as Quentin said, if you think about it, linear 1 is what? 3072 to 20, right? But then after that, the data still needs to go through an activation, which you can think of as wrapping around. So this is the activation 1. So what comes out of that is, that's the end basically of that hidden layer. And so you can do a normalization there before the input goes into the next hidden layer. Do you guys understand? So how would you do that here in the code? You would then do X equal self norm, right? Your own norm. So norm of X. You see that? And of course, you have to then define that as self dot norm. And it's probably, if I remember correctly, it would be NN dot, and I think it's layer norm. Do you guys understand? So this is what I'm talking about. So you're going to have two sets of things that you're going to do. Either things like this, right, into your architecture, plus also making the models deeper. If you make them deeper, believe me, you want to add more normalizations in there. Okay? Is that concept clear? All right. So that's one thing you want to do. And then the other set of things is just basically create new architecture. So that's, we're going to create, like I said, a DLNet and a CNN basically. All right. Yeah, go ahead.
Convoluted neural network, that's what CNN stands
A
for.
what, sorry?
A convoluted neural.
It's a convolutional neural network. It's a more complicated algorithm.
So I'm finding.
Yeah. I'm going to show you how to implement it in PyTorch. What's important, as I said, is that you see how all these things work. So, because they're really the things that will allow you to get higher results. Okay. There's only so much you can get out of an MLP. And then there's only so much you can get out of an actual DLNet before you need to go to a CNN. And there's only so much that you can get out of a CNN before you need to go to something called transfer learn. Do you see that? So all of these things are needed, and also these ideas of normalizations, etc. Got it? All right. Remember, these are just hints, right? So let's go over here. So it finished, I believe. Okay, so it finished training, right? So let's look at the performance. And it's better from 0.11 to 0.14. Yeah, go ahead.
Change there was 1.13 or 0.13.
I didn't change anything.
Oh.
Don't expect that the models will always give you the same answer. You can think of it as there's some kind of a randomization going in there. So that's why it's a good idea to run multiple runs, so that if you run 10 of these, the average can be trusted. You basically on average will always get that value. Do you see what I'm saying? So this is just the same architecture. Guys, any question? Making sense? All right, so that's it, right? So now let's go ahead and start defining a new architecture, which is going to be a DLNet architecture, okay? So I'm going to create here, I already have this. I'm going to reuse basically this code, and you guys can help me to craft a new architecture. Now you're going to craft a neural network. So the problem with this is that, like I said, it just becomes way slower, right? It takes longer to train. And so that's the problem. But, we're going to do it. So let's change the name. So this is the MLP-net. So now we're going to do a DLNet, for instance. DLNet. And let's just say this will have 3 hidden layers, okay? 3 hidden layers. So how do we do that? Okay, so one thing we know is that it's going to start with 3072. So this doesn't change, and it's going to end with 10. So that doesn't change, right? But we need to have inside 3 neural network architectures. Three neural network architectures, so that's the input. What that means is there are 3. Okay, there are going to be 3 in there. And so how do we create that? So I'm going to separate it out like this, so it's easy for me to see. Okay, I'm going to change at this point the activations to be ReLU activations. We need to talk about what that means, but basically that changes whatever the output that comes out of the network into a value that is going to be between 0 and the maximum. Okay, so basically it cuts out negative values. That's what ReLU means. Okay, so if I have -3, 0. But if I have 15,000, 15,000. Do you see that? That's effectively what it's doing. Yeah, go ahead.
And is there any benefit to having multiple activation functions? So like, hey, I want to run ReLU, then I'm going to run SigMod or something, or vice versa.
You can try it. I mean, it's experimentation. In general, ReLUs are some of the best for classification. So they're the recommended rule of thumb.
And if we somehow ever have our own bootleg activation function and it works, can we use that?
Yes, definitely. If you win, do that. Okay, so let's go ahead and build DLNet. Okay, so I'm gonna change this to relu. Just want to make sure I don't give you errors. So this is lowercase e and everything else is uppercase, like that. Then I'm going to create another layer. So we need to define like the size of it. So 3072 initially. And 10 over here. So what are good sizes for the hidden layers? Hidden 1, hidden 2, and hidden 3.
1,000 maybe.
1,000. Remember, it takes a long time to train something that big.
So basically, to my not, so basically trying, you want, so those dimensions you're looking for, you'd probably count like, I don't know how many.
I want these, the
Right.
number of
Like
neurons.
the first one, right?
Let's start here, yeah. This is 3072 for sure.
How many, like, in the image? Like for example, like, if you're doing like faces or something.
This
you
has
don't-
30, this has 3072 neurons.
Right, and I'm just saying, like, what can you extract from the image manually? Like, I don't know, like say like facial features, for example, like, oh, this person has like a large nose or something, or like,
Yeah.
what is the symmetry of the face or something like that, or like,
I wouldn't even don't.
but like if you like, I was saying, like, if you like have those, probably have some sort of like way to like, oh, these are the things I really care about, multiply that by like a certain factor or something, and just use that.
I would say this is a really big image. I want to run this quickly and debug it. So I'm going to start with small values, funnel them, and then look at my performance. If my performance is not good, I'm going to have to scale up. Generally, a finding in the last 5-10 years is more data, bigger model, more compute, equal better. Okay? So this has been found by Facebook and Google, and things are getting really big. All right, so then I would start at most with 200 here, at most. And that's gonna, as you probably will see, will take a while. Okay, but that's ideal maybe. And then just scale it down a little bit if that's taking too long to run. So with your GPU, right? So then go maybe for 100, 50, and 20, or 30, for instance. All right, so make sense? This is kind of how you should approach it. Yeah, go ahead, Eric.
So the last number, 10.
Yes.
For any other model will be like really small, right? So depending on the number of hidden layers, you would want the values to be closer to that ending value.
Right, you funnel them. So you want to funnel it, and you don't want to give it too much space to like think.
There's like a big difference. 200 and then 10 and 200.
Right, but here we don't go directly. We go from 372 to 200, for instance, or 100, yeah. But this is a big jump, actually, from 3,000 to 200. But that's actually, I think, reasonable. Yeah, for this data set. Yeah, Henry.
Would there be any cases where your next layer is larger than your previous layer?
For images, I usually haven't seen that.
Okay.
So for
But
instance,
not images, I guess. Would there be any case?
maybe, but in general, the funneling is a good rule of thumb. Okay, it's almost like I said, just don't let it procrastinate. You know, force it to be efficient, and the neural network will be efficient if you force it. Yeah, please, Mark.
What sort of graphics cards are we getting for this calculation?
What sort of way?
You said 200 is the limit. What sort of graphics card is
The GPU?
Yeah.
It's right here. It's it's an NVIDIA. It's A30s or V100s, I believe. Tesla V100s. These are pretty good cards. Yeah, so these are good. Okay. All right, so let's go ahead and let's just build this architecture. Okay, so we're doing 3 hidden layers, right? And this is really important that when you picture a neural net, that you know how to write it in PyTorch. Okay, that's, I would say, one of the most critical things. So DLNet, 3 hidden layers. Okay, so I have this. This is the last layer, right? So I need at least 2 more. I'm just gonna do that, right? And you guys can help me out with the dimensions. So this is linear 1, this is gonna be linear 2, this is gonna be linear 3, this is gonna be linear 4, okay? And that's important that the names change because the dimensions are gonna be changing, okay? So definitely it starts at 3072. Then let's say ideally 200 neurons, ideally. Activation function is ReLU. What is that? Remember, you have the layer, and then it's really like what comes out of it goes through that. But in general, what people do is they just wrap the activation around this. So it kind of makes sense. Like this is the final state of the values. And so those values need to go through the activation, which is ReLU. Does that make sense? And it's really just changing. That's not a normalization. That's just an activation. Okay. It's almost like in the theory is probably like in the brain, right? Things are happening, but if you don't meet that threshold, nothing is activated. So you activate until some threshold is met. It's met, and it goes through that function. Okay. So it's a type of intuition. So now here we have linear 2, right? That's going to be for the next one. So 200 to 100. You guys see that? Okay, and that also is a ReLU activation. Make sure you change this to 2. That's usually what I do. And then I'm going to change this to activation 3. Okay, so then this one would be what? 100 to 50. Got it? With its own ReLU activation as well after. If you don't put these ReLUs in there, that's not a neural network. It seems like a very trivial thing, but it's just it's what it's called a linear model. It's just like, doesn't matter how many hidden layers you have. If you don't have the activations, it's not a proper neural network. Yeah.
Is there something substitute for ReLU that can make it work better?
Other activations, there's one called a GELU. I mean, uppercase, I think.
What's a jello do?
It's a Gaussian ReLU.
So it's just like,
It calculates a mean and a standard deviation also.
so it would just be like
in the
Gaussian, making some variables of Gaussian noise or something?
It's calculating what does Gauss do? Mean and standard deviation, right? So it's calculating those parameters and using them in the activation.
Okay.
But usually I mean for the long, that's one of the newest ones, but usually ReLU has been a workhorse that people trust. Okay. But try others. There's sigmoid, tan-H, GELU, ReLU, newer one, leaky ReLU. There's one called leaky ReLU. Go ahead.
Can you, when you, I guess, set that up, can you use multiple? Like, for example, can you use ReLU and then GELU and then the other one?
I guess, but I haven't seen that. No. So you might use it, but like it was not gonna break. But I don't know that there's an advantage. Yeah, go ahead.
Are different activation functions useful for different networks?
For a different one?
This one,
Yeah, this is a classification. ReLUs do really well in classification, for instance. Yes, that's a good question. Tan-H, for instance, creates values between -1 and 1. Sigmoid creates values between 0 and 1. ReLU creates values that are positive, basically. So any negative is dropped and becomes 0, but positives remain. So there may be some situations where you actually want -1 + 1. Guys, Henry, did I answer your question? Yeah. All right, great. All right, so we want to create this architecture, right? So we are at 50. Now we do linear 4, activation 4. This is going to be 50 to 10. Do you see that? And that's it. Draw your diagram and then write the architecture exactly like this. Now, one important thing that you should not change is this one here. That last activation should not be a ReLU. In fact, don't play with it. Just use the softmax, okay? The softmax is a very interesting concept. We'll do an example later. Also, when I start breaking all of these things down into, you know, the little things that they do, it's an activation like the other ones, but a different kind of activation. So the intuition of this is as follows. You might have a vector of 4 classes, right? And basically that's going to be some values. You would want, so let me actually, I need something to write on. All right, hold on. All right, so I'm going to do the whiteboard here. How do I get the classical board? No, it's they changed this. It's not the oh, okay, there we go. Sorry. So they changed this whiteboard like today. And I had this problem in the other class that I need to switch to the classical view. I don't know. Okay, sorry about that. Okay, so what happens in the neural network, right? We have this one that we've been trying to build. Okay. So all of these have had a ReLU activation. The last one, though, I said to you to not use ReLU, instead use the softmax. So you might ask, what is that exactly, right? So basically what you have to think, one thing that we know about this is that you define that there are 10 neurons here. Each of these is for one of the classes. So essentially what the neural network is learning to do is to provide what is called a probability distribution. So what does that mean? It basically means that as this comes out, it's going to be a vector of 10 values, okay? Which you can think of them as probabilities. So they will look like 0.6, 0.4. This is for the CIFAR, 0.2, 0.1, 0.7, 0.3, 0.09, 0.05. How many is that? So this would be class 0, 1, 2, 3, 4, 5, 6, 7. We still need a few more, right? So 0.1, 0.1. So that's 8 and 9. That's it, right? Because we started at 0. That's 10 classes. Do you guys understand? So let me just finish this thought. So what needs to happen once you do this is the neural net gives you this, but you still need to take one more step, which is basically to say, which one of these is the highest value? And then the one that has the highest value, you can think of it as saying that's the highest probability class. So here, which one has the highest value of these? 6, right? This one. So then basically the class would be 6. So you're saying, you know, class 6 has the high, this image has the highest probability of being class 6. Do you guys understand that concept? But what's one problem if you look at these values here, at all of these? If this is a probability distribution, it should add up to 1. And this does not add up to 1. Do you see that? I intentionally made like just these two are 1 already. So the model would be better. Now, if you think about the real data, does the real data have a probability distribution of 1? It does. Why? Well, I'm almost afraid to go to another page here. All right, so let's go to another page here. So what does the real data look like? If it's class 3, right? In theory, that's going to be a one-hot encoded vector, right? So class 3 would be 0, 1, 2, 3. Do you see that? So this value would be 0, this value would be 0, this value would be 0. That's a 1. This is, and the other ones are zeros. If you sum all these values, what do they add up to? 1, right? So it's a probability distribution that adds up to 1. All of your, intuitively, you have to think of it like this, right? Theoretically speaking, every class that you give the neural network, think of it as you're giving it as a one-hot encoded version of it, right? I give it, let's do it like this now. The last class, class 10, because it starts at index 0, that's going to be 9, right? So the last class, 9. Let's say that's a cat, okay? So you're not going to actually give it 9 in theory, right? The neural net is producing vectors of size 10. So that's what you would compare to. And so this would be a 1, but all the other ones are 0, right? That's what's called one-hot encoded. If you add up this distribution, adds up to 1. So what you want to do is you want to give the neural network also the ability to create a distribution that adds up to 1. Do you guys see that? So then going back to the previous example here, we need a way that once this vector comes out of the neural net like this, it needs to go through another function, and that function changes those values so that they add up to 1. Does something exist already for that? Yes. And it's called the softmax function. You see that? So you always use the softmax function, and the idea is almost like this. So we can, let's do another final example of this. I will do a simple Python code next week just to show you how softmax works, and I'll convince you that it does do it. But so let's think of it like this. So we have here real data coming here, right? So 0, 1, 0, 1, 0, 0, dot, dot, all of these are zeros. So that's 0, 1, 2, so that's the class 1, cat. That's what's coming in, adds up to 1. You're going to compare this, right? In the loss function, you compare, let's say compare to what comes out of the neural net. So here you have the last hidden layer, hidden 3, and then that becomes the vector that comes out, output of size 10, but that still needs to go through the softmax, so that it gets modified to a vector where now, when you add it up, it will also add up to 1, okay? So both of these add up to 1. Add to 1, and this definitely, you can see, adds to 1, right? You know that. So then what those values that we had before will be modified to be something like, I'll just make up some numbers, but it should look something like 0.05, 0.05, that's 10 already. 0.020, that's 30. 0.10, that's 40. And then that 0.7, right, that we had seen before, remember that 0.7? I hate this new. So this 0.7 thing would still be the highest just within that distribution that adds up to 1, okay? So that's basically the only thing. And that's, I think, a really important intuition so that you understand why softmax is necessary. So that 0.7 might now be 0.30 because it's still the highest. You see that? So 0.30. So this is 10, 30, 40, 70. 70, and let's just say these are all 0.05, right? But essentially, that's the one that you would pick, and they add up to 1. Yeah, go ahead.
And those are all probabilities.
They're not technically probabilities, they represent probabilities.
Would, if they would like.
The neural net is telling you that you're definitely going to pick the one that's the highest of those to be the class.
With like the softmax function, that piece that was like a Bayesian optimal classifier.
No, it's an equation. Like literally, you will see it's a simple equation that just convert. It's like a mapping of the numbers to another set, and they do add up to 1. I promise. It uses e to the something to do the calculation. I will do this next week.
Sorry. And but sorry, one team sorry, that's after we do the softmax, right?
Softmax is so the vector comes out here from the neural network. And believe me, it's going to be numbers that don't add up to 1.
Right.
So then that vector goes through a softmax, and all softmax does is it forces the numbers, like it rescales them so that they add up to 1, but in relation to what came out of here.
And then you just choose which one has the highest probability to return that label.
Yes, exactly. But when you're doing the training, you're that's why I wrote compare. So you compare the vector that comes out of the network after it goes through the softmax with the actual one-hot encoded labels. But the intuition that you should not forget is that because you're one-hot encoding this, all the values are 0 except the one for the class. So it adds up to 1, right? There's no question about this. So this one should have the same property to be a better model. Otherwise, you're not as efficient. Got it, guys? Does that make sense? All right, so that's why that's important. I don't change that one, or your model may not work. All right, so let's no. How do I stop share? Close whiteboard. All right, now let's switch back to this. And let's continue with our architecture. Okay, so we are defining a deep net with 3 hidden layers. So I have done this one, right, to 200, then the one for 100, and then finally the one for 50. So it should be finished, right? So that's the definition of it. But now we have to implement it in the forward function, okay? So what am I going to do? I'm going to take this norm out. I'm also going to comment it out. I'm not using this right now. So linear 1 to activation 1, then I can just copy this. And that's going to be what? Linear 2, right? linear 2, activation 2. Got it? Right? And then linear 3, activation 3, right? We can get rid of these spaces. I mean, not necessary. Okay, and linear 4, which is the final layer that gives us the result, right? And that is activation 4, and this one must be a softmax. Got it? The dimension 1 is because you're going to be feeding it batches. So there's, rows and columns. So you want to do the softmax across the columns and not across the rows. If you wrote dimension 0 there, you'd be doing the softmax across the batches and not the columns. Make sense? That's it, right? So I think that's it. That's a deep neural network right there of 3 hidden layers. Isn't that pretty easy to do? Right? And so now, obviously, this should take longer. So let's try it out. So we need to instantiate this. So control copy. I'm gonna run it. Okay. And the beauty of this is all you have to do, change that, and now add model equal beyond that. That's it. And everything else works because of the way it has been written so that it's like very modular. You see that? And now we can train with a deep neural network. Let's try it, but I'll probably have to stop it because it's going to be pretty slow. So let's go ahead and try this. I'll just run it from the beginning. I usually like to clear the kernel. Sometimes the model stays trained already, and then it would continue to train. All right, let's go. Let's give it a minute to catch up. Yeah.
Do more layers, longer runtime, but
Yes.
better results though?
Yeah. Again, I'll repeat this because it's a finding from the last 5 years. More data, bigger architecture, more computational time equal better model.
We can get more data.
We get the better of the two.
You mean in CIFAR?
In this.
That's right. That's right. That's true. Yeah, I see where you're going with it. Yes. So you're limited to data. You can't do anything about that. Okay. Architecture, you can add as much as you want, but the more architecture you add, the more computing you need, more compute, right? So maybe instead of 1 GPU, you need to run your job on 5 GPUs in parallel. You see what I'm saying? Or be willing to just wait for hours on 1 GPU. But yeah, pretty much. But unless you have your own GPU, see, if you have your own GPU, you have an advantage because you don't have to deal with a 2-hour limit, right? You see the problems of this world? These are very real problems. To the point that the United States is probably thinking of creating like data centers just because, like free ones, because it's necessary to compete in the world. So anyway, all right, so let's keep going. Let's keep going. So let's run. Okay. We're gonna try the new architecture and see if it breaks. Okay, so I already loaded the architecture. Hopefully I didn't miss anything. Okay, here's where I instantiated. Okay, nothing. And then here's the training loop. So let's wait. Yeah.
Can you show us how to do a checkpoint while we're
Yes, I don't have the code for that. So
Oh, we need to.
yeah. Give me next week and I'll provide. Yeah, but it's basically from model save. But I want to do it correctly. So that's a good point. So I'll do that. All right, so it's training right now. And I'm printing, I think, every 5 epochs, right? So let's see if this takes longer, but you know, it is a big neural net. Still might take a while. All right, while it's doing this, I will introduce another thing that you can try in your architectures, right? So remember like the normalization. Oh, here we go. So there's one. All right, so now let's go back to, let's say the MLP. Let's go back to the MLP. Yeah. So another thing that you have available besides these layer norms is something called dropout. This was invented, I believe, by Geoffrey Hinton as well. Geoffrey Hinton, by the way, as we will see next week, is the father or the godfather of AI. He invented basically gradient descent, the only algorithm that is used to train neural networks. Okay, so he also developed this idea of dropout. So let's see if I can do a good job here in explaining how it works, but it's a nice one. All right. So again, just like I added this layer norm and I told you that you could add it at the end of each hidden layer, now also at the end of each hidden layer, you can add another thing called dropout. So we're going to do self dropout. Oh, sorry. That's the name. And then we're going to invoke nn dot drop out. And I'm going to say 0.2. Hmm?
I think it's still drop.
Oh, yeah, sorry. Dropout. Yeah. All right. Yeah, thank you. So that's a construct basically from PyTorch. How do you use it? The same way that you use layer norm. At the end of each hidden layer, you can invoke your dropout. So you would do something like x equal self dot dropout x. Okay. What does that do? It's actually really interesting and valuable. So you guys understand probably at this point that you should try different architectures, right? What if I try, so here I said 200 to 100 to 50. But then you're thinking, what if I do 300, 250? But then I can also do 225, 125, 50. But then I can do 226 and 227, right? You see, and then are you going to do all of those? Probably not, right? Dropout has this property that it is like doing that, but just by adding this simple line of code. And it's like a very elegant solution. So how does it work? So let's switch over to the board again.
Like a scalar?
It's not a scalar. It's randomly disconnecting some of the neurons. Right?
Okay.
So let's think about it.
And it's also training
Along during the training, it's trying different architectures basically. Just by
the best.
It keeps the best one, yeah. And it's effectively like trying different sets of neurons because it's randomly dropping by that probability that you define. Do you guys see that? So let's think of it with one simple example on the whiteboard here. So I think I just
that would be like a 1 in 5 chance of dropping each neuron.
Probabilistically, yeah, up to 20% of the connections it'll drop. But let's look at an example, right? So let's say that I have a simple one here. Right, and I just have like, 5 neurons here, and I have like 4 there, right? This is the input. This is the input. This is the hidden layer for that. So this is going to be fully connected. So what that means is that you have an architecture of 4 to 5. But as it's training, what dropout does is let's imagine all the connections here. Assume, please, that this is fully connected, okay? So during dropout, it's gonna say, okay, 20% is removing that one, and that one. That's a different architecture, isn't it? Now this neuron, for instance, is no longer connected. So you now have an architecture of 4 instead of 5 for this run. Does that make sense, guys? That's what dropout does. It's a very elegant solution because then the network, it's gonna just have this architecture to get an input, run it through the network, predict the value, and compare it to the real. And the weights are changed according to that. In another scenario, as it's training, you once again have fully connected. Right, imagine that's fully connected. And now dropout is going to once again say, okay, those. Do you see that? And once again, it feeds inputs, they go through the net, they come out, get compared with the real, and the weights get updated. But with these, some of these connections effectively removed. And that basically means, you know, it's equivalent to having different architectures here because that neuron is not connected anymore. Think that this is a simple example of just 5, but what if you have 300 neurons there? Think of 20% of that, right? And it's trying these architectures. I mean, it's obviously not trying every possible combination, but it's better than the one fixed architecture you have, for sure. Got it? Do you guys understand the concept? All right, so yeah, so that's dropout basically. Something that was you know, and created by Hinton and his team, and it's something to try. I can't say that it's going to give you better results or not, that you're going to win or not, but try it. Okay, because the intuition is you're trying different architectures in a sense. But that the parameter is usually left at around like 20%.
And you don't want to go like higher.
Yeah, because then you're breaking too many connections, basically.
And at that point, you might as well just like shrink your.
Yes, exactly. Exactly. That's actually a good point. It's like you set a network and then it's like it broadens it a little bit. You know what I mean? Like it opens the range of it a little. That's actually a good, I like that. It's not basically like going from one architecture to another very different one. It's more like sticking with the one that you kind of have, but broadening the, you know, the way that it is.
It's basically noise to make sure that not everything's off of one, right?
Yeah, it's just more flexibility for the neural network than the one fixed architecture you have defined. Got it, guys? So this is yet another technique that you can try, okay? You can also try the leaky ReLU, which is, where did I define? Oh, ReLUs were defined here. So leaky ReLU should just be, so here, I'll change this one. It's leaky ReLU. And if I remember correctly, the zeros, sometimes it lets it be a little bit negative. So it just gives it a little bit more, right? So ReLU is always 0 or positive. And I think if I remember correctly, leaky ReLU has a little bit more on the negative.
Is there like a benefit to that or?
Henry, I'm just saying, try these things. This is the whole point, right? You guys will try all of these things to see if you can win. And there's quite a few more of these techniques. But in general, I would say layer normalization is really important. If you make really deep neural networks, then there's something called residuals. But we'll talk about that later. It's actually very easy to implement, but it's a complicated idea to think about. So let me state it like this. 0.5 times 0.5. What is that? 0.5 times 0.5. 0.25. 0.25 times 0.25.
0.012.
Okay. 0.0125 times 0.0125.
Point taken.
You get it, right? What is happening to the result? It's getting smaller every time, right? At some point, we have 0.00001. Do you see that? Well, that analogy scales to deep neural networks. the deeper it's actually in the reverse, actually. You can think of it in the reverse. So you go forward and then you back propagate. So as it's coming back, 0.5 times 0.5. The next one, 0.25 times 0.25. The next one, 0.0125 times 0.0125. But what if you have a very deep neural net of 128 layers? By the time you get really close to the inputs, effectively those values are what? 0. This is called the vanishing gradients problem. And this is on when they created deep learning algorithms, or very deep, they encountered this problem. But they have now solved it with something called residuals, which allows you to have very deep neural networks. So the point is, one of you may have the brilliant idea, because you have a GPU at home that's amazing, that you're going to have 100 layers of these, right? And you might think that's going to give me really good results. But if you do something like that, it is too deep. And remember, the gradients are vanishing, which means the weights, eventually, if you have all your weights are zeros, it doesn't work anymore, right? You guys see that? So for those of you that are going to try very, very deep neural networks, you need something called a residual, which is similar to these little things here. After every hidden layer, you need to put a residual. Yeah.
And the end vector, which you said wasn't really probabilities, but can be thought as like, almost like not really representation, but something more like a subset or something like that.
Yeah, it's not technically a probability, but it's telling you which one is the more
And
likely.
they're all like close to 0. It doesn't really tell you much about the data set, right? Because like
The what, sorry?
like if they're all like so you have very
The probabilities, no, one of those, if you have a good model, one of them should be really high and close to 1, and all the other ones should be very close to 0.
right. And the problem with all of them being very close to 0 with one, only I don't know. Actually, no, that can be possible.
No, that's actually a good thing. You want your neural network to make one of the values 0.95,
Right.
and all the other ones should be 0.005.
I was
That's what
thinking-
you want.
I was thinking the case of what if like all of them are like close to 0, but that could be the case for the all.
Then you have a bad model. If
Yeah,
all of them are 0, then you haven't learned anything.
Right, because you have to like add. You need all of them to add to 1.
Remember that the model needs to create the one hot encoded vector. And the one hot encoded vector has all 0s except for a 1 in one of the classes. So if you've trained your model well, one of those values is like 0.9899, and the other ones are 0.00 something. But that's a different thing from the vanishing gradients that I was explaining, right? Those are two different concepts. Does that make sense?
Yeah.
Intuitively, though, what I'm saying to you, just making 100 layers does not mean you're going to have a good neural network, because there is that problem, which but can be addressed with the residuals, for instance. Got it, guys? If you notice, it's still training. Let's take a look. And it only is at 25 iterations. So it takes a while, all right? But let's keep going. All right, so we've done now the DLNet and it's running, right? So what's the next thing that I recommend as a hint? As something called a CNN. What is a CNN? I will briefly next week cover intuition of that, but that is an advanced, that gets you into the space of advanced deep learning algorithms. So that's more than just a deep neural network like the one we're building here. That's something called, the CNN algorithm. So that, there's several algorithms above this. So this is just like the end of what you can do with just deep learning. And then after that, you start making special algorithms that build on top of this, but they are different in some way, right? And that's really CNNs, generative adversarial networks, or GANs, and transformers. Oh, and there's also RNNs, recurrent neural networks. So there's only like 4 main advanced algorithms, but they're very powerful. So how powerful are they? Well, maybe those of you that correctly implement a CNN will get way better results than those of you that only implement at DLNet. You see what I'm saying? All right. So now let me show you how to create a CNN, right? So we're going to go over the architecture of it. And then later, I will give you a little bit of the intuition of where that's coming from. Okay. So how do we do that? Once again, copy your class here. We'll copy. Just like that, right? And we're going to change the name, obviously, to CNN. CNN net. Okay. Let me just grab my architecture for that. All right. So there's another way of, and also this gives me an opportunity to show you another way of creating neural networks. Okay, so this is going to be slightly different. I'm going to use, in this case, the construct called NN sequential. Okay, it's a little bit different, if you will notice, from the previous one. All right, so we still have our forward and our init functions in our class. So our constructor and our forward function. But I'm going to change the way that I approach this. So I'm going to remove these, okay? And instead, I'm just going to say, yeah. So I'm going to say here, ypred equal self dot model. Okay, so I'm going to initialize this model using the NN sequential for the CNN. It's just sometimes this is more convenient, especially when you're building something very long. You know, you want to, this is easier, I would say. Also, of course, you need to provide here the input, right? So the batch or whatever it is, X. Got it? Everyone with me? All right, so now then, in the constructor, basically, we're going to build the architecture. So right here. All right, so I'm going to say self.model, and I'm going to use nn.sequential. It's just another way of building the neural net. As the name implies, now you can just throw all the layers here in sequence, and that's it. Things will go through them, okay? Like I'm going to put in a whole bunch of lines. So assume that the X comes in here and it goes all the way down. Yeah.
Is this called sequence model?
No, this is just like a programming construct. Okay. Nothing to do with sequence mining. That's not, you know, time series data. That's a different thing. Okay. We're building a CNN. So do you guys understand though? So what I was doing before of doing this sequence, this sequence here and passing the X's, notice that here I would give it an X and pass the X to the other thing. And then you see that difference? We're not going to do that anymore. We just have to put in the lines in here. And as long as they're in that order, the X will go through them. Got it? That's the approach. And I use it when I build really long things because I'm kind of lazy. All right, so how does this work? So basically, when you do CNNs, you are not going to use linear functions anymore. Instead, you change linear, right? At the NN linear here is going to change to another thing for CNNs, and that is called the conv2D. Okay, so I'm just going to define this. So this neural network will have 2 convolutional layers and 1 feed-forward layer, basically. So maybe we should build a neural network architecture first. So I'm going to do this. Go to the whiteboard again. Okay, we need to do that. Like the pen. All right, so now, what do we know? Our images are still coming in through the input. However, one important difference, our images now can come in as grids. Does that make sense, guys? So you don't have to spaghettify them anymore. There's an advantage in that, in the sense that CNNs can run faster actually than a spaghettified deep neural network. So that's also an advantage to consider, not just performance, but also an implementation wise, it may be faster, okay? So, but yeah, so the images come in through here, and now we're going to define two convolutional layers. One normal neural network layer feed forward, and my output of 10 classes. Do you see that? So this is going to be very similar to what we have done, but here we have these convolutions. So what is a convolution intuitively? Just so that you understand. A convolution intuitively, since now we have actual images. Oops. We have actual images. You can think of still a matrix multiplication, but it's a different kind of a matrix multiplication. You have now this concept of a filter, and you have the actual image. So what's going to happen is you perform the same matrix multiplication between this image and the filter. And what it produces is another representation of the image. That's it. That's what the neural network does. Do you see that, guys? That's what's called a convolution. So basically, think of it as the image gets the filter, and the filter looks at this part of the image, and it's going to transform it somehow into something else. Then the filter moves, it looks at that part of the image, and it's going to transform it into something else. And it just continues to do that until it reaches the last part of it, remember this filter, and it transforms it into something else. And you do this many, many times. So for instance, you can say, I'm going to apply that filter 32 times. And it can be different filters also. And what are these filters? Does a human go in and define 32 individual filters? Well, actually, that's what people used to do 15 years ago. People would spend careers creating one filter in a decade for images. But what they discovered is that the CNN can learn what the filter should be. That's the amazing insight about it. Is that so basically this is a neural network because this is just values, right? There's just numbers in there. And those numbers are learned by the neural network, and they're basically weights, just like before. But it's a different kind of an operation, if you think about it intuitively, that is running filters through the image and producing a new representation of the image. So 32 new images, basically. And those are passed to the next convolution and so on. But the filters initially have, so this is obviously the image, so that has the normal values. But the values in here initially are random. But because you have a lot of training data, you're running and running and running, and those weights are being learned, right? So think of it this way. You give it an image, it's got random values here, produces a new version of it, that goes into several layers, predicts a class, predicts bird, it was a dog. Bad filter. Try it again, image, another set of weights in the filter, produces another image, predicts a bird, cat. Bad filter. But it's learning, right? Next time around, another image, filter has better weights now, produces an image here, another version of the image, whale, it's a whale. Good set of weights. Do you see that? And so it starts to, the point is that for whatever your task is, these filters are going to be optimized. Do you guys get the intuition of this? We'll come back to it a little bit later. I just want to do one example here of something called edge detection, right? So in edge detection, what do you have? Imagine that you have a furry animal. A furry animal. So furry, right? Furry, and then background, white background. Do you guys see that? So what do you expect about the pixels of this image? Here, all of these pixels are probably 0 or 1 or some number like that because it's the background. But what do you expect about the pixels where it's furry? They're going to change a lot. This is going to be a 55, that's a 57, this is a 60, this is a 65, this is 67. So how do you detect edges? Well, if you look at this one, it's 64, 70, 50. These are all changing. So if I look at these, right, and I average them, and then I look at these and I average them, it's always different numbers. So that allows me to know that's something, a pattern. Over here, it's another pattern, and I can notice the difference. Do you see that? Where the pixels change completely. So for instance, if I zoom in on this now, this is 60, this is 22, this is 21, 30, 70, 0, 0, 0, 0, 0, 0. So I can notice where this transition happened, and therefore I can flag all these pixels as an edge of an image. Do you guys understand that concept? We can do it in Python later if you want, but the point is that we don't have to create filters that do this. Instead, we let the neural network figure out what those filters are that produce something like this that helps in the classification. And it doesn't have to be an edge detection. It's going to be something more sophisticated than that. And because we do layers, think of it this way. Think of it this way. This layer of the convolution finds edges. And that is fed, into the next layer. So what the next layer gets is not the original images, but the filtered images where it has detected edges. And now it uses that to keep understanding what the image is about. Do you guys get that? Does that make sense, guys? Well, any questions? All right, so hopefully that made sense. So now let's build the architecture for this one, and that should be enough for today. So I need to close here. Go over here. All right. So we are building, notice that it's still training. So here in NN sequential, I'm going to define my convolution. So I'm going to say convolution 1, con 1 layer, or con layer 1 actually. More appropriate. So then I'm going to say NN dot conv 2D. Okay? That's what the construct is in PyTorch to do that thing that I just described. So it needs to have certain parameters. 1 for emness, because grayscale. So if you're doing RGB, which you are in CIFAR, this probably needs to be a 3. Do you understand that? Yeah, okay. Then you specify how many filters you want. So 16. You have to specify them somehow, because it's going to affect performance of the GPU. Yeah.
And basically the 16 part, that's the number that you need to manually try to calculate, which is the optimal. Or is like what is like a natural number?
Remember, this is going to impact GPU time. So if you pick 2000, it takes way longer, more weight.
Like say if you do 2000, would it be like really good, but it'll take super long time?
Maybe, yeah. It's think of the number of weights, right? A lot of weights. So 16 here. Also, it's not necessary for CIFAR-10 to have something that big. Then the kernel size equal 5. What is that? I drew the image and I drew a little filter. What that 5 just means, it's a matrix 5 by 5. Do you guys understand? Remember, initialize to random values, but as you're training, those values get changed, updated to be the optimal weights. Okay? then you need to specify the stride here. I like to specify stride equal 1 because then I use another function called max pooling. And it's just how I prefer to do things. If you specify stride 2, for instance, then you don't have to use max pool. Okay. But that's kind of the idea. But max pooling is the funneling effect. So what does that mean? You have an image that is 32 by 32 by 3, right? You're running it through 16 filters, and now you're producing 16 images that are 32 by 32 by 3. That just exploded in size. Would you agree? And if you keep doing that, it keeps exploding. So max pooling just means, you know what? I need to control that somehow. So what you do at the end of every convolution is cut those images in half. Do you see that? So 32 by 32, 1. Now 16, 32 by 32, max pool it, so it's now 16 by 16, right? Yeah. So you cut them in half. Does that make sense? And it's the funneling effect. You're forcing the neural net to be more efficient with its weights, okay? It works. All right, so we do the stride padding. We're gonna set it to 1 in case like it needs to have padding, but we don't need that probably. Okay, and then comma. So NN relu. So that means that the values that come out should run through the activation. Does that make sense? Just like before. Whatever comes out of this convolution, those values are going to get modified via the relu function. Notice that it's different now, right? Before, I give it an X, comes out here, that becomes the input to this one, and so on. This one doesn't require that because I'm using NN sequential. Okay. It's just going to go through all of these one by one. All right, then NN max pool. Oops. Max pool. And this is 2 by 2, and that will cut it in half, basically. Okay.
So basically, so the NN sequential is basically like a list, like functions. You just iterate through the list, you just apply it to the function.
Maybe, yeah, more or less.
Okay, but like the idea is generally that, right?
Yeah,
Okay.
yeah, you can think of it that way. You can think of it. That's actually a good analogy. All right, now I'm going to do the next one. So remember, I just finished convolutional layer 1. Now I'm just going to copy this one, do convolutional layer number 2. Remember, this did edge detection. This is going to do more sophisticated with the previous. All right, so this is going to be con2D. Now this needs to be 16 because this was 16, okay? And then you want to specify the number of filters. So now I'm going to do 32, more filters, okay? You can play with these parameters. So it's entirely up to you. You can change the stride, but I'm going to leave it at 5, or the kernel size, sorry. The stride at 1, because I want to use max pooling. I'm going to use relu, and I'm going to cut it in half, basically. So pretty much the same. Got it? Right. And then the last part is I need to do a feed forward. So that's just like a regular linear one, like the previous ones, but those are called feed forward. Just so that you hear that term. It's just like the previous one. And that's going to be NN dot linear. You guys see that? NN linear. So that is usually from the convolution to a hidden layer and from the hidden layer to a final output. Okay, so that means this is, I need to define the size of that hidden layer, right? Do you see that? The convolution comes out, feeds into a hidden layer of a specific size that I'm going to define, and from there it goes to the output. You see that? All right, so I'm going to do 512 because I'm the architect. That's my choice. I'm going to copy relu here. And then now should come the last layer. So that's going to be.
What was before the common? Does that mean like there's no? Like,
Oh, I need that. I haven't addressed that because that's difficult.
Is it like a Python?
We need to, you're asking about this, right? We need to solve that, and that's not easy. But give me a sec. So we'll wrap up with this, okay? So NN, we're almost done. NN dot linear. Is that, yeah, linear. So this one you should know how to do because it's just a 512, comma 10. Do you see that? So that's the end of it. And of course, this needs to have a softmax. Another, let me use another one. There's one called the log softmax. So either try them. Soft,
And log softmax is just like the logarithm of like the method.
pretty much. And then remember the dimension because you don't want to do it over the batches. You want to do it over the. Now, Henry, because I'm short on time. We got a problem here. We need to know this input. But what do we know? It's coming out of a convolutional neural network. And that is what? Batch by filters by some dimension. Would you agree? Yeah? Because remember, it's the image that was 32 by 32 by 3, right? But then it became 32 filters, but then it became max pool, so it was cut in half. So, and that's not a vector, by the way. Does this expect a vector? Yes. This expects a spaghettified thing. So what do we need to do? We need to spaghettify it. So that's going to be NN dot flatten, which is, another way. Like that. So this will take whatever this is, it's a hypercube of some kind, a tensor, and it's going to flatten it into the value that goes there. The question is, what is that value? You see that? So you need to have code that will tell you what that number is because you have to hard code that. So in my example, let's just add a number here, 800, let's say. But you will need to calculate that value. I'll show you how to do that, but next week. Do you understand, guys? Is this intuitive? So remember, this comes out as a cube from the convolutional layer, but it needs to be flattened so that it feeds into this. And yeah, and so if we go to our original architecture, which I think went away or something. So we had done the input, the convolution, this is the output of size 10. What comes out of here is a cube, a hypercube actually. But we are specifying a hidden layer here of size 512. So we needed to connect it like that, right? From 512 to 10, that was easy enough. But the 800 to 512 is because this needs to be flattened into something. And so that would have essentially like 800 for it. But that's actually something that requires a special calculation, which is straightforward. And I can show that to you next week. That's it. Once you have this, you can, instantiate the CNN and basically go from there. Does this make sense, guys? Are there any, any questions? Yeah, Quinn.
How are you saying that the convolution layer 1 is going to edge stitching?
How am I saying that?
How is it going to?
I mean, that was an example. I don't actually know what the filters are doing. So there's 16 filters, right? One of them could be edge detection.
Okay.
If that is helpful to classify the samples correctly. But remember this, it's not random. It's actually, that's where the intelligence of AI comes in. Because you and I can create maybe in a whole lifetime 10 filters. The neural network can create hundreds, and they're better. You see that? Because it's going to try this filter. It's going to run it. Does it work? If it works, hey, that's a good filter. Does that answer your question? Yeah. All right, guys. so we can stop here for today. Please start working on the CIFAR-10. You have all the elements now. And then I'll just keep at this point drilling down into all these concepts. So today we kind of started doing that. All right, have a good weekend.